Hello everyone, my name is Pratyush and I welcome you all to this video in which I'll be showing you my final IBM Capstone project for the advanced data science specialization that I've been doing over the past few months. And my capstone is titled as Forecasting the Highest Stock Price of an RIC over Time with Advanced Machine Learning. Coming to the project goals, the end goal is basically to build a time series forecasting model that predicts the daily highest price of any given RIC for the upcoming 6 months. It performs time series analyses based on historical data from January 2019 to September 2023, and based on that, it predicts for the next 6 months. Throughout the process, I also try to determine what features will have the strongest impact on the daily highest price, then cross-validate two models. One is a random forest regressor from the machine learning stack, and the other one is an LSTM recurrent neural network from the deep learning stack, or the neural network stack, you can say. So what I wanted to do was I wanted to choose one model from machine learning, one from deep learning, and compare their performances with each other and get an idea of what would be the more suitable stack for time series analyses in general and for business applications. And finally, I deploy the best performing model with the best configurations and hyperparameters as an interactive and user-friendly Flask-based web application that takes an RIC ticker as a form input, and on clicking the submit button, it generates a chart.js visualization, a line chart in chart.js that has the forecasts for the next 6 months until March 2024. So coming to the dataset, this was an open source dataset extracted from Kaggle. It has two files, a stock data and sector data. Stock data has prices from January 2019 to September 2023 for the highest price, opening price, closing price, and the trading volume. And sector data is basically a referential data set that has sector related information for each RIC, such as the company name, economic and business sector names, industry names, etc. etc. So this is an overview of my full stack life cycle of the data product. It involves three main phases. That is the EDA, exploratory data analysis, in which I perform data quality checks, univariate analysis, finding the frequency distribution, outliers, multivariate analysis, that includes correlations and the behavioral trends between two or more variables. After that, the second phase is the ETL, or the extract, transform, and load, in which I cleanse the data based on the EDA recommendations, transform them, handle the nulls, drop duplicates, rename the columns, aggregate them for better representation, such as like what I did was I aggregated them over the RIC month and year and found out the average highest price, closing price, opening price, and the trading volume. And the next second part of this is feature engineering, in which I find the most important features to the target variable. And as you know, the target variable is the highest stock price, followed by the most important part, which is building these two models. One is the random forest regressor, as I just mentioned, and the LSTM neural network. Cross-validate their performances, do regression testing on them, and finally deploy the best performing model as a web service in Flask. So these are some EDA results. As you can see, the data was full, like had a very high number of nulls. So we had a total of more than 500,000 rows and 6 columns. So basically from 2019 to 2023, we have around 500 instances. There were around 15,000, more than 15,000 duplicates, which were duly handled by straight away dropping them. For the nulls, it was a little bit more complex. Complex in the sense I needed to handle the nulls based on the distribution so that I do not incur any information loss. So to do that, what I did was based on the frequency distribution, I found out that these continuous variables, they follow a very skewed distribution. They're not normally distributed, and at the same time they have a lot of outliers. So I cannot impute them with the mean because mean is outlier sensitive and assumes normal distribution. So I handled nulls by first dropping all the records in which the date column was null, because if we do not have a date, then it basically becomes a noise. How would you predict it for the next date when you don't have the current date in the first place? So I remove the null dates, and from that I impute all the nulls in the continuous features like the opening, closing, highest prices, and the daily trading volume with the median. Because as I mentioned, cannot do it with the mean since it's not normally distributed and has a lot of outliers. And I also do not I did not want to incur any information loss. So straight away dropping these nulls would lead to that circumstance. And mode imputation is mostly done for categorical features, and here we are imputing for a continuous feature. So median was the most prudent choice. Then in the multivariate analyses, I found the correlation metrics. In the correlation matrix, you can see that the opening and closing price have the strongest correlation to our target, that is the daily highest price. And comparatively, the volume has a significantly lower correlation, under 50%. So we can say that these two impact the opening and closing price impact the highest price the most. But there's also a possibility of multicollinearity if we use these two features. Multicollinearity occurs when we try to predict a target variable using highly correlated features that might not add more information to our analysis. In that case, in order to handle any possibility of multicollinearity, what I do is I create a new feature called the daily return. This daily return is basically the difference between the opening and closing price for a given day, and it's also an important financial measure in stock markets. So I add this to my feature set, and in the next part I found out the feature importance of each variable to the target in the feature engineering phase. And what I found out was that the opening and closing price contribute to approximately 87 to 88% of feature importance, which shows how highly important they are. Compare that to the daily volume, which has an under 10%. So it's not wise to use them in the feature set. Might might lead to a loss in information. So it's not a relevant feature at all. The average daily return, while it does not have a high feature importance, it's a derived feature that we have got from two highly important features. So it may be useful, it may be not, but we could always test them with different combinations. So I came up with two combinations. One feature set is opening and closing price, and the other one is opening price, closing price, along with the daily return. I tested for both these combinations, and I found out that while their performances were very similar to each other, the first combination was slightly better. So this is what I went forward with. So these are the two models, the model architecture for the random forest, like how I create the feature vectors, scale them, define training and testing data. So for this, I've used an unconventional train test split rather than using 70-30 or an 80-20 split. What I've done is I've defined my training data as the data from January 2019 to September 2022, and my test data as October 2022 to September 2023, because I wanted to include their time series and sequential nature in the train test split as well. So that is how I defined them, and then I implemented the necessary steps for random forests, like finding the hyperparameters, fitting them on the train and test data, checking for overfitting and underfitting, evaluating their performances. And then in the LSTM, I did this after defining the training and test data. I charted a different course, that is building the lag sequences for the 12 for based on the previous 12 months, because we need to include the historical aspect of the time series data. Find out the appropriate number of layers, so that this is how we define it. Suppose if we want to predict for the next 6 months, so the number of layers in the LSTM would be n plus 1 7, the current time step and the following 6 time steps, depending upon how much you want to predict. Then I implement early stopping on my LSTM model. This is done in order to prevent any possible overfitting and find the optimal number of epochs. What early stopping would do, once the optimal number of epochs is reached, it would not run beyond that and hence prevent any overfitting beforehand. Then the same thing, I evaluate their performance on using various regression testing metrics. So the regression testing metrics I've used are the RSME, the root mean square error, mean absolute error, the mean absolute percentage error, and we can clearly see that the LSTM is the superior performing model. And especially if you look at the mean absolute percentage error, the difference is very big. The random forest is generating a percentage error of 430%, which is very high and very inaccurate, whereas LSTM only has, it could have been lowered, but it's still decent, has around 18 to 19% of percentage error, which is like way more accurate than the random forest. And this was somewhat expected because regression models usually do not perform well on time series data, and this is what I was trying to find out, why why they don't. The reason being, regression models fail to capture the temporal or the seasonal aspects. By this, what I mean is, suppose if we want to predict for the next 6 months, or not the next 6 months, let's just say for the next month, it'll always be dependent, or there will be a strong impact of the data from the past 12 months, past 6 months, or any past historical data in time series analysis. So this temporal nature must be captured in a model to come up with the next few months forecasts. What the random forest model or any regression model fails to do is capture this temporal aspect. It just takes in the feature vector and predicts it. But for the upcoming months, there are no feature vectors. So that's why it's giving such a big error. And on the other hand, LSTM addresses exactly this part. It captures the seasonal aspects by creating lag sequences on the feature vector and predict, and comes up with the prediction for the next month or the next 6 months, depending on how much you want to predict. And finally, I would like to show you my data product. This is the web application. You input the ticker name in the form, click on the submit button, and here we go. The forecasts for this ticker for the next 6 months, along with the company name and other information like the economic sector name, business sector name, industry name, activity name, etc., etc. And this is how it does. This is a chart.js visualization. It's a lightweight library, does not add a lot of resource overheads, and is also like very interactive. You can hover over each data point and find the exact value, which is the average highest price for that month. So this is what I wanted to show you, how I deployed my final data product for for my Capstone project, how I deployed my neural network model as a usable product for end users. And I would like to thank you all for staying tuned with me. Please like, share, and subscribe. Leave your comments. I'll be giving my Gmail and my LinkedIn in the description box. Feel free to connect with me, share your feedback, your critical reviews. Everything is welcome. And thank you all for listening to me and staying tuned with me. And hope you all have a great day. Thank you.